To understand why any chemical bond forms, we have to look at the universe's preference for stability. Atoms will combine and interact specifically to reach their lowest possible energy state, primarily by completing their outer octet of electrons. In an ionic bond, a metal completely transfers outer electrons to a nonmetal. Here, sodium gives its lone 3s electron to chlorine to form sodium chloride. Similarly, calcium transfers 2 electrons to fluorine. This is the Born-Haber cycle for sodium chloride. Notice the massive downward arrow labeled lattice energy, U. This represents the immense energy released when millions of oppositely charged ions lock into a vast, rigid crystal grid. While simple electron stealing builds incredibly stable crystal lattices, this model fails to explain how nonmetals bond with each other without a clear giver or taker. In reality, no bond is 100% ionic. According to Fajon's rule, a small, highly charged positive cation will physically distort the electron cloud of a larger negative neighbor. As the cloud distorts, by pulling that electron density back toward itself, the bond develops a partial covalent character. For pure covalent bonds, we use valence bond theory. In this model, atoms mutually share electrons. As the spheres connect, two atoms bring their half-filled atomic orbitals close enough to physically overlap, creating a distinct shared region where their electrons pair up. As the view shifts, the shape of that overlap determines the nature of the bond. A direct head-on connection creates a standard sigma bond. But if p orbitals overlap laterally, side by side, they form a pi bond. Simple orbital overlapping makes sense for two isolated atoms. However, it is insufficient for predicting the actual 3D shapes of more complex molecules, like the 4 perfectly spaced bonds found in methane. A carbon atom's valence electrons sit in mismatched 2s and 2p orbitals, 1 sphere and 3 dumbbells. But in a molecule like methane, all 4 bonds are identical and at equal angles. To achieve this symmetry, the atom mixes those distinct orbitals to create 4 identical balloon-shaped sp3 hybrid orbitals arranged in a tetrahedron. As the formula slides in, you can determine an atom's hybridization by calculating its steric number. Simply add the number of attached atoms to the number of non-bonding lone electron pairs. Lone pairs are crucial because they dictate the final shape through VSEPR theory. Unbonded electrons repel each other more strongly than bonded pairs as the angle compresses. When a bulky lone pair replaces a standard bonded atom, its dense cloud physically pushes the remaining bonds closer together, squishing the internal angle from 109.5 degrees down to 107. Hybridization and VSEPR together provide the mechanical framework to predict the physical three-dimensional architecture of almost any chemical compound. Yet, even with accurate geometry, localized sharing theories leave glaring gaps. For example, liquid oxygen is highly magnetic. Valence bond theory suggests all its electrons are safely paired up, which would make it non-magnetic. This chart is a molecular orbital diagram for oxygen. Molecular orbital theory argues that atomic orbitals don't just overlap, they merge entirely to form new molecule-wide orbitals. As the diagram populates from the bottom, this creates lower-energy bonding orbitals that hold the atoms together, and higher-energy anti-bonding orbitals that push them apart. You calculate the overall bond order by taking the bonding electrons, subtracting the anti-bonding electrons, and dividing by 2. For oxygen, this yields a double bond. Crucially, it also reveals 2 unpaired electrons sitting at the very top of the energy ladder, the source of liquid oxygen's magnetic properties. By treating electrons as quantum waves that span the entire structure, molecular orbital theory resolves the physical properties that earlier localized models could not handle. Beyond primary bonds, molecules also exert forces on each other. Hydrogen bonding is an exceptionally strong dipole interaction, but it operates under strict conditions. Hydrogen must be directly bonded to nitrogen, oxygen, or fluorine. This interaction can happen intermolecularly, bridging separate molecules together and driving up boiling points. Or it can happen intramolecularly, causing a single large molecule to fold and bond with its own tail. By layering these theories, from ionic lattice energy to quantum MOT diagrams, we possess a comprehensive method to predict how any matter in the universe interacts. Each model solves a specific layer of the chemical puzzle.